So, good evening, everyone. We are at week 10 of problem solving session for analog electronic circuits course. So, in today's session, we'll be yeah we'll be talking about like starting with mirror circuits. So, we already discussed mirror circuits, right? In last week. So today also let's see some problems based on mirror circuits. So in this first problem, here we have a cascade current mirror circuit with all four MOSFETs being matched to one another and all are NMOSes. And here Kw by L is given as 1 milliamperes per volt square. VTH of all the transistors is 1 volt. Lambda is 0.01 volt inverse. Supply voltage is 12 volts and reference current is 2 milliamperes. So, refer to the circuit given. Now, find the DC voltage V3, that is drain to ground voltage for the MOSFET 3, such that the current flowing through M2 or M3 is exactly 2 milliamperes. So it is given that, let's say it is, I write it as ID, okay, ID3, ID2. So it is given that ID2 is 2 milliamperes. The transistors are matched and they're also in saturation. So if I write the current equation for transistor M3, ID is ID3 is Kw by 2L VGS minus VTH whole square. Now here and also ID2 is Kw by 2L VGS minus VTH of whole square. 1 plus lambda VDS will also come, right? So this is for 3 plus lambda VDS for 2. Why? Because lambda is not equal to 0, so we have to consider the lambda. Now here, if we observe very carefully, what is the voltage V3? V3 is actually VDS3 plus VDS2, right? V3 is VDS3 plus VDS2, correct? So if somehow we can find out the values of VDS2 and 3, we can simply substitute them and we'll get the value of V3. Now here, if we observe very carefully from this image, okay, so we'll paste it. So here, what are the things we know? This is source, drain and gate, drain, gate and source. So if we observe very carefully for M1 and M4, VGS is equal to VDS, correct? There's no doubt, right? Because this is in a diode configuration, right? So now, when this is in diode configuration, and we know the current flowing through M4 transistor, that is ID4 is how much? Kw by 2L. VGS minus VTH of whole square 1 plus lambda VDS is the current that is flowing through transistor 4, which is equal to 2 milliamperes. Now here your VGS and VDS are equal, so which will give us like kW by 2L VGS minus VTH of whole square 1 plus lambda of VGS equal to 2 milliamperes. kW by L was 1 milliamperes. So 2 milliampere equal to 1 milliampere per whole square by 2 into VGS is something that we don't know, correct? VGS is unknown for us. So VGS minus VTH is 1 whole square 1 plus lambda is 0.01 VGS, right? This is what we get. So let's cancel. So it is like 4 VGS square minus 2 VGS plus 1 into 1 plus 0.01 VGS. So 4 equal to VGS square minus 2 VGS plus 1 plus 0.01 VGS cube minus 2 0.02 VGS square plus 0.01 VGS, so which becomes 0.01 VGS cube plus 0. VGS square minus 1.99 VGS minus 3 equal to 0, correct? So this is the expression that we get to calculate VGS. Now by solving this equation, we'll get the value of VGS, and basically we'll get 3 values, right? So can you quickly solve, like anyone has a scientific calculator, can you quickly solve and see like what are the values that we are getting? Okay, so the values that I'm getting for VGS are minus 99.96 after solving this equation, okay? And VGS is 2.97 and VGS of minus 1.01. So out of these 3 values, what is the actual value of VGS?
2.97.
2.97, right? So VGS is 2.97 because other values are, first of all, they are negative and we have NMOS here. So we should get a positive value. So that's why other two will be discarded. So we have VGS as 2.97 volts. Now here, since all the transistors are matched and same current is flowing through all the transistors, so what will happen when we are going for our voltages? So all the transistors will carry the same VGS, right? So the VGS for M1, M4 and M3, M2 will be equal. Like VGS1 equal to VGS2 equal to VGS3 equal to VGS4 equal to how much? 2.97 volts, correct? Now, we also know that for transistor M1, M4, your VGS is equal to VDS, right? So similarly for the other side also, for transistor M2 and M3 also, your VGS should be equal to VDS, right? So that your transistors are perfectly matched and same current is mirrored. So hence your VDS1 equal to VDS2 equal to VDS3 equal to VDS4 equal to 2.97 volts. Your V3 is VDS2 plus VDS3, right? 2 and 3, yes. So which is 2 times of 2.97 volts. So that is V3 is 5.94 volts. So this is the value of V3 that we are getting. Okay. Now here we definitely considered the lambda, as lambda was not 0. So we considered the value of lambda and calculated the currents and everything accordingly. Right. Now moving on to the next problem. And again the same. Yes.
In last problem, all transistors are on, ma'am.
Sorry. All transistors are on.
Why, ma'am?
All transistors are on and all transistors are in saturation. So first of all, the moment you have diode configuration, that is gate and drain are shorted. So when gate and drain are shorted, your VDS is definitely greater than your VGS minus VTH, right?
Okay, ma'am. Okay, ma'am.
So which is
I was thinking about this M3 and M2, but they are due to current mirror, it also in saturation.
Yes,
Like
yes.
that. Okay, ma'am. Thank you.
So that is happening because of this mirror circuit. Otherwise it won't be possible. So this is because of the mirror circuit. We are getting like all the transistors are in on state and all are in saturation also.
Okay,
So moving on to the next problem. So in this particular problem, we have find the small signal output resistance looking into the drain terminal of transistor M3 for the circuit shown below. So how do we write the output resistance or output impedance? So we look from this node and we see, okay, what are the like components which will come into picture. Now here again we have first of all this current mirror like diode configuration, and then we have two transistors in cascade fashion, like one transistor connected to other. So the source is connected to drain of another transistor, right? So in this type of configuration, how do we write Z out? So these things are like you can also analyze, and these are already analyzed in lectures, and also you can visit the lectures. I'm directly writing the formula. So it is GM3 R03 into R02 plus R03 plus R02. So this is what the formula comes out for this type of configuration when you have two transistors in cascade and their gates are like in mirror configuration with diode connections. So there, this type of resistance we will observe, or output impedance we will observe. Now here we know that R0 is 1 by lambda into ID, and GM is also known, that is 2 times of IDS into KW by L, right? So we'll simply substitute the values and calculate, like R0 is 0.01 into 2 milliamperes and Gm is root under 2 into 2 milliamps into 1 milliamp per volt square. So this will give 2 millis. This will give us 2 millisiemens, and here R naught we will get as 50 kilo ohms. So Z out will turn out to be 2 millisiemens into 50 kilo ohms into 50 kilo ohms plus 50 kilo ohm plus 50 kilo ohm. So it is Z out is like millikilo cancel. Fifteen to 100 kilo ohm plus 100 kilo ohms. So that is 5 mega ohms, like approximately equal to 5 mega ohms, right? So this is the Z out that we observe for this particular circuit. Now moving on to the next problem. So in this problem, it is like referred to again the same circuit. Find the minimum DC value of V3 with which small signal resistance remains high. Okay, what should be the minimum value of V3? So minimum V3 should be how much? So what is V3? V3 is VDS3 plus VDS2, right? If we say, okay, what is the minimum condition for V3? Then V3, minimum conditions for V3 means minimum conditions for saturation. So for VDS, what is the minimum condition? VDS min should be VGS minus VTH, correct? The minimum value for VDS should be VGS minus VTH. So VDS minimum of 3 will be VGS 3 minus VTH, that is 2.97 minus 1, so it is 1.97 volts. And now similarly for this particular transistor, if we say like VDS to minimum, how much can it be? So your okay, it can be written as like this VGS. If we write, okay, let's say V3 can be written as VG min, VG3 min, or VG3 minus VTH3. Now, if we see like the gate potential over here, what is the gate potential? So it is like this potential till ground. So if we observe, it is VGS plus VDS, right? So we can write it as VG3 as VGS, let's say 4 plus VDS 1 minus VTH3. So V3 min is 2.97 into 2 minus 1, so which is 4.94 volts. So this is the minimum voltage which is required at this particular point V3 to keep all like your transistor M3 as well as M2 in saturation. So yeah. Maybe this method is much easier, so we can ignore this method. So it needs a little more analysis, but since this is a easier method, so let's go with the easier method. So here simply V3 you can find by Vg3 minus Vth3, where Vg3 like can be written as your VGS4 plus VDS1. And since VGS4 and VDS1 are equal, so we will simply write down their values, and we'll get the minimum value for V3. Now, coming to the next set of problems. So in this problem, this is again a CS amplifier using current mirror circuit. So for PMOSs, this is a PMOS, NMOS, NMOS, and PMOS. This is the current mirrors part, right? This is the current mirror part that we are talking about. So now the question is, okay, KPs are given, KPWL. KPW by L is 1 milliamperes per volt square. KNW by L is 0.25 milliamperes per volt square. And VTH, mod of VTH is 1.5 volts. Lambda is 0.01 volt inverse. VDD is 10 volts. And the current flowing through the drain terminal of M1, okay, and or M2 also. So for M2 also it is 2 milliamperes. The current flowing in this branch is 2 milliamperes. The transistors M1 and M2 are identical. So these two PMOSs are identical. Similarly, transistors 3A and 3B are identical to one another. So transistor M1, M2, M3A and M3B, they are identical to each other. So PMOSs are identical to, so both the PMOSs are identical and both the NMOSs are identical. Okay. Now with this information, refer to the circuit given in this figure and find the ratio of R1 by R2, which is these resistances, and their ratio with the ratio of R3 by R4, so that the nominal current of 2 milliamperes is flowing through the MOSFET M1. So to obtain this current of 2 milliamperes, what is the ratio that needs to be maintained between R1, R2, R3 and R4? That is the question. So here, yes. In this, first of all, we are performing DC analysis, correct? So since it is a DC analysis, this capacitor will not come into picture. And if we have like 10 volts over here, so your gate voltage at for transistor M1 will be determined by these resistances like R1 and R2. So, and also if you observe very carefully, transistor M1 and M2 are matched, right? So if M1 and M2 are matched and they are carrying same current, that means your resistor R1 by R2 should be equal to R3 by R4, correct? So that VG1 is equal to VG2. VG2, correct? This is must. This is something that we already know. Now, if we observe, okay, like ID1 is KW by L, KPW by 2L, VGS minus VTH whole square, and 1 plus lambda VDS. So let's say for now, this 1 plus lambda VDS term is very small, right? This is very small compared to your 1. So lambda VDS is much smaller than 1. To just simplify the calculations, nothing much. So ID we can write it as KPW by 2L VGS minus VTH of whole square, and from here your VGS1 will be root over 2 ID by KPW by L plus VTH, mod VTH, right? Now here we know all the values, that is 2 into current was 2 milliamperes, Kp was 1, Kpw by L is 1 milliamperes per whole square plus 1.5, so which gives us VGS1 as 2 plus 1.5, that is 3.5 volts. So the gate voltage VGS1 is 3.5 volts. Now if gate voltage of VGS1 is 3.5 volts, and the same gate voltage should be applied to your transistor M2 as well, so which is also equal to VGS2, that is 3.5 volts, right? Now okay, so in this figure, if we observe from transistor M2's perspective and M3's, transistor M2 and M3's perspective, we observe that 2 milliamperes is also flowing through this diode connected NMOS, right? So for transistor M3A, VDS3 is equal to 3A is equal to VGS of 3A. This is something that we already know. Now here your VDD is already given as 10 volts. So again 2 milliamperes will be KNW by L, Kn by 2 W by L, VGS minus VTH of whole square. Considering that lambda is very small, so we are ignoring that. So VGS will again come out to be 2 into 2 by 0.25. Here it is 0.25 plus 1.5 volts. VGS is 800, 200, 4 plus 1.5. So VGS, we are calculating 3A, 3A, 3A. So it will be 4 by 10 plus 1.5. So VGS 3A is 4 plus 15 by 10, that is 1.9 volts. VGS 3A. VGS 3A is 1.9 volts, and this VDS 3A is equal to VGS 3A, right? VDS 3A is equal to VGS of 3A is equal to 1.9 volts. Now, if 1.9 volts is the drop across this point to ground, so your drop across this point to ground is given as 1.9 volts. Your VGS is VG2 minus VS2, which is 3.5 volts. So VG2 equal to 3.5 volts plus 10 volts. If it is for transistor 2, it will be VSG. VSG2, so VS minus VG22. So it is VS2 minus 3.5 is equal to VG2. So it is 10 minus 3.5 is VG2. So VG2 is 6.5 volts. And if VG2 is 6.5 volts, then your VG2 can be written as R4 by R3 plus R4 into VDD. So VG2 is also equal to R4 by R3 plus R4 into VDD. So that is 1 upon R3 by R4 plus 1 into 10 is 6.5. So 3.5 by 6.5. So the ratio which was asked was R3 by R4, which is also equal to R1 by R2, is 3.5 by 6.5. Now this analysis that we did, we'll use it later in later parts. So anyways, yeah, moving on to the next problem. So in this problem, again for the same circuit, we have to find the value of DC output voltage, V out, as shown in this figure. So this V out is something that we need to find out. So what we said that both the PMOSs are matched, both the NMOSs are matched, same current is flowing through them, they have same gate voltages. So your VDS will also be same. So this VDS and this is also VDS, right? So these two VDS will be same. So VDS 3A is equal to VDS 3B. Here we already calculated VDS, right? Something is wrong here. VDS minus VDH. Oh, yeah, there is a mistake, right? Here it will be 1. Yes, 1. So this is 4 by 1.5. So it is 5.5 volts. So here it is 5.5 volts. Here also it is 5.5 volts. Yes. So we know VDS 3A is 5.5 volts, so which is also equal to VDS 3B, which is 5.5 volts, and this is also equal to V out. So this we got from the analysis which we did here. So maybe I'll do one thing. Since this analysis was for the next problem, so maybe we can transfer this. It could be a better idea. Yeah. So this is how we got the answer. Yes. So this is clear, right? How we got the value of VDS and hence the V out. So we use the simple analysis of mirror, and since here there was a diode connection, so VGS can directly be related to VDS. So we could simply relate it over here. Now coming to the next problem. So in this, in this problem, we have to find the small signal voltage gain. In this problem, small signal voltage gain in mid frequency range, that is the maximum gain that you can get basically. The coupling capacitor is assumed to be shorted in this frequency. So this is shorted. Now what will be the gain of your circuit? So it was already mentioned that this is a CS amplifier. Yes, so this was mentioned that it is a CS amplifier with current mirror, definitely. But for CS amplifier, we know that the small signal gain is GM into Z out, right? Now for this, at this point, if we observe like, okay, what is the Z out? So it is due to this transistor M3B and M1. So that is Z out is R01 parallel R03B. And GM will be due to your GM will be due to PMOS because the input is in PMOS. So GM always comes from the transistor which provides you the input, like from where you are giving your input. So that transistor will give the GM. So the transistor that is getting input is transistor M1. So your GM will be because of M1. So GM1 is root over 2 times of ID1 into KW by L, which is rated to 2 milliamperes into 1 milliampere per whole square. So that is 2 millisiemens. This is GM1. R0 is lambda 1 upon lambda ID. That is 1 upon 0.01 into 2 milliamps which is 50 kilo ohms. So Z out is for both the transistors, your R naught will remain same as the currents are same. So it is 50 kilo ohm parallel 50 kilo ohm. So we will get 25 kilo ohms. Now Z out is 25 kilo ohms. GM is 2 millisiemens. So our gain is 2 millisiemens into 25 kilo ohms. So gain is 50 volt by volt. So the gain that we obtain for this particular circuit is 50 volt by volt. Now coming to, yes, you can unmute and ask if you have.
Ma'am, VGS1, how can you calculate, ma'am? Because it is not in saturation. VGS1.
VGS MOSFET M1, you are saying it's not in saturation.
How can we calculate that VGS1? Because it is not in saturation.
No, it is in saturation. Like, first of all, the idea is whenever you are analyzing an amplifier, it is always like while you are designing, you make sure that all your transistors are in saturation. While you are solving the problem, you assume that all the transistors are already in saturation, because amplification you will only get when all the transistors are in saturation. Otherwise, you won't get the amplification operation.
Then what will be value of VGS1, ma'am?
We calculated VGS1, right? Here, the first problem. We knew the current, and from there, we knew VTH, we knew current, we knew the constant. So we
Okay,
calculated
ma'am. Okay, ma'am.
VGS1, right?
Okay. That one current we know only for a below transistor, na, ma'am. If they are in series.
No, so see, whatever is the current, since all the transistors are in series, so same current will flow through all the transistors, whichever are in series. So if it is said that your transistor M2 carries a 2 milliampere current, that means your transistor M3 must carry a 2 milliamperes current. Similarly, for transistor M1, it was mentioned that it carries a 2 milliampere current. So the same current will also flow through transistor M3B since they are in series. And there is no path where you can distribute the current.
Ma'am, what if M1 is in linear region, ma'am?
No, it will not be in linear region. Like if it is in linear region, like for amplifier operation, always all the transistors in the circuit are made sure to be in saturation region. Even while designing also, if you are designing an amplifier, you make sure that all the transistors that you are using should be in saturation region.
Okay, ma'am.
Yeah. So that is the idea with which we start solving. So that's why we like you must have seen, like we never used any other current equation, right? Because if we would have like linear transistors, the current equations change there, but we never used that. We always use the saturation current equation. No, that is because for amplification operation, your transistors must be in saturation. So that's why.
Okay.
Hope this is clear. So yeah, with this, let's move on to the next set of problems. In these problems, now we are done with the mirror circuit based problems. So we are moving to the analysis with capacitors again. So in this particular circuit, CS is 3.1 volt, 1 picofarad. RS is so this is 3.1 picofarad. RS is 43 kilo. Your GM is given. GM is 1.47 millisiemens. RDS is given 30K. CGS is 7.4 picofarad. Okay, with this much of information, it is asked that the overall transfer function is to be evaluated for this given circuit. And for this, use the Norton's method. What is the pole due to the output impedance? Give your answer in megaradians. So what is the pole? What do we understand by pole? What is a pole? How do you find the value of pole? Here it says pole due to output impedance. So how do we write that pole? Yes, what is the value of pole? We discussed this, right? What is the value of a pole? We said that a pole is 1 upon RC at that given point, right? So let's say here it is asked what is the pole at the output. So at this output, we should find the R out and C out, and we'll like take 1 by RC of that, and we'll get the value of pole over there. So now first of all, Z out. So this is the drain node, this is source, gate. So if I say in this particular circuit, what is the R out that we will observe or Z out that we will observe? It will be 1 upon Gm parallel RS parallel RDS. Right, at this particular node, if we observe, the values that we'll get is 1 upon Gm RS and RDS. So now here we know the values of like 1 upon Gm is given. So from there we can get like thousand by 1.47. So this is 1 by Gm is 680.27 ohms. So 680.27 ohms parallel to 30 kilo ohms parallel to 43 kilo ohms. So the Z out will turn out to be very close to your 680 ohms. Because in parallel combination, the resultant turns out for the lowest, turns out to be the lowest value. So that's why. So here, what is the value of Z out that you'll get? Like 680 parallel 30 parallel 43K.
$16.72.
How much?
16.7K.
16.7K. The parallel combination of all three. So Z out is 655 ohms. Because see, in parallel combination, the idea is whatever is the smallest value, you'll get even smaller value than that. That is the idea of small like parallel when you calculate parallel. So here
Then
it was.
how, ma'am, then how it will be less than 17, ma'am? How it will be greater? Actually, smallest is 17K, so it should be
Oh,
less
how
than
is smallest 17K? Smallest is 680 ohms, right? See,
I
units
thought
are very important.
680K. That's right.
No, no. That's why I was saying, no, it is ohms. So units are very important. That's why I'm saying. Okay. So it is 655.05 ohms for Z out. Now, similarly, we have to calculate C out. So what are the C out that what is the C out that we will see? So one is the CS that already is there. So CS parallel to this CGS will be a Miller capacitance. So we will get one part in the like input and other part in output. So the output, the value of capacitance becomes like CGS times only, single CGS. So it is CS parallel CGS. So in capacitance, parallel combination means addition. So we'll simply add 3.1 plus 7.4. 3.1 plus 7.4. So that is 10.5 picofarad is the C out. Now we have got Z out, we have got C out. So the pole in radians per second is 1 upon 655.05 into 10.5 giga. Let me pico. So here it will be 12. So the value that we are getting is 145.39 megaradians. Megaradians per second. So this is the value of pole, which is option B. Right? Now, it is asked that what is the value of zero because of the short circuit current that is appearing. So how do we find zeros? So I guess we discussed it once before, but let me reiterate it again. Number of poles is equal to number of AC nodes. The number of AC nodes that you have in your system, that many number of poles will appear in your circuit. Second, number of zeros will be given by number of capacitors connecting your input and output node. So for zeros, the idea is you calculate the number of, like you see how many capacitors are there between your input and output node. So number of capacitors between input and output nodes. So these are the two things which are very important. So kindly keep this in mind whenever you have to calculate poles and zeros, rather than solving like transfer functions, huge transfer functions. This is the easiest way you can find the values of poles and zeros. First of all, check for AC nodes. The number of AC nodes you have, that many number of poles you will get. And from there, you can find the dominant pole, which is like the value of R and C, the largest values of R and C. So the pole 1 by RC will be smallest. So that is the dominant pole. And for zeros, how many capacitors are connected between your input and output? So definitely you have one input and one output. So how many capacitors you will get? Only one capacitor, right? So you'll have 1 0. Majority of the times it is 1 0. So yeah, and sometimes it might be possible that there is no connection, no direct connection between input and output. Let's say if the circuit was somewhat like this. Okay, here you are taking your output. This is the transistor you are giving your input. Is there any link between your input and output? No link, right? So if there is no link, like there definitely will be a capacitor here and here, here and here. It will be there. Definitely it will be there. But since these points are not your output points and they're not connected between input and output, so you won't be seeing any zero. In this particular case, between your input and output, you have one capacitor connected. So that particular capacitor will give you a zero. And what is the value of that zero? Again, zeros are also calculated by 1 upon RC at that particular node. So here at the input node, what is the input resistance and what is the input capacitance? That will give us the zero value. So at your input, like between your input and output, the capacitance that you have is C is CGS. Now what about R? What is the R that you see over here? The R that you will observe here is actually GM. Okay, 1 by GM. The R that will appear because of this capacitor, which is connected between input and output, will be 1 by GM. So basically, the 0 will have a value of minus GM upon CGS. 0 will have this frequency of GM upon CGS. So the value of 0 will be, we already knew the GM, 1.47. CGS was 7.4. So this will be 7. Mega radians we have to report, okay. Here it is millisiemens, right? 10 to the power minus 3. Yes. (198.65 megaradians per second). So the value of 0 that we get is 198.65. Clear? For 0, like the resistance that we observe is 1 by GM and capacitance that we observe is CGS, which is the capacitor between the two nodes. Okay. So if even if you like calculate the complete transfer function and equate your numerator to 0 and denominator to 0, you will get the poles and zeros. But after simplification and all, you will observe that you will get the same values that you are getting from these formulas, like 1 by RC. You can check. So what you can do, you take, let's say, take this problem only. For this, draw the small signal model, find the transfer function. In that transfer function, you equate your numerator to 0 and denominator to 0. So numerator to 0 will give you a 0 and denominator to 0 will give you a pole. Now, if you do certain simplification, or if you calculate the exact values from there also for poles and zeros, you'll observe that the values for poles and zeros are very close to these particular values which we are directly getting by using 1 upon RC. So you can try work out on this exercise. So that's why it is an easy method. So let's say if you have a huge circuit and it is very difficult to write down the transfer function, calculate the transfer function. So it is more of like a shortcut to find the values of poles and zeros at a given node. And it gives almost similar result or equivalent results. So it is not far away from the exact results. So you can check this out. Okay, now moving on to the next problem. So in this problem, in a practical situation, a common drain circuit is going to be used to buffer a signal source with large source resistance. Consider the circuit below where the input resistance Rs is 43 kilo ohms. GM of the device is 1.47 millisiemens and CGS is 7.4 picofarad. Now assume the common drain circuit is driving an infinite large impedance. Okay. It is driving an infinitely large impedance. So it is like, okay. So this is the load. Now for this load, this could be an assumption where we are trying to just work out the Thevenin-Norton model. Okay. Now further assume that RDS of the device is also infinitely large. So RDS is infinite, making GDS equal to 0. Now ignore the body effect. So what is the magnitude of output impedance of the circuit at a given frequency of 3.2 gigahertz? So your circuit is given, all the necessary information is given. So why don't you try this problem? Let's say give you 5 minutes. I'll take a short break and come back. Meanwhile, you try this problem and let me know how will we approach. Okay? Take your own time. Okay. So yeah, maybe last minute. Okay. Any ideas? Like how would we approach anything that is coming to your mind? So finally, we want to find the output impedance. And since it is an impedance, so like there will definitely be a capacitive component, and capacitor is already there. So in that component, you will fit in the frequency and get the value. But what to do, where to start? No ideas? Nothing coming to mind? Okay. So first thing, whenever it is asked, okay, what is the output impedance? What we'll do, go to very basics. Let's say you are applying a voltage Vx, you are applying getting a current Ix from that voltage source. Your Z out or Zx will be Vx upon Ix. So the target is to find this Vx upon Ix. If we find the Vx upon Ix, our task is done. We know that the transistor provides some current ID, right? And mind you that whenever you are applying a source, like here, let's say you are applying a Vx, you cannot have Vn simultaneously. Okay, so at the time only single source will be in action. So that's why we are shorting this source Vn, and we'll only see the effect on the circuit due to this Vx. Clear? Now, ID is the current flowing from the transistor, Ix is coming from the voltage source, and let's say in this path I1 is flowing through the capacitor all the way from capacitor to the resistor. So, like if we write KCL, how the KCL will look like? Ix is I1 minus ID, correct? Ix is I1 minus ID, right? ID we know it is GM VGS plus GD VDS. It was already mentioned that GD is 0. So ID is GM into VGS. If you observe very carefully for the given transistor, this is VG, this is VS. So VGS can be written as VG minus Vs, which is Vx or Vout, right? Now, how would you write your VG? What is VG? So if I say, okay, VG is, this point is Vout, right? So VG can be written as R upon R plus 1 upon Cs into Vout. Can I write it like that? This is node V out or Vs, and this is Vg. I'm simply applying voltage division as there is no current flowing through the gate of the transistor. So I can write Vg as R upon R plus 1 by Cs into V out, or we can write it as RCS upon RCS plus 1 times Vx. This is Vg. So we got our ID in terms of Vx, that is Gm anyways, Gm RCS upon 1 plus RCS minus 1 times of Vx. So ID is Gm into RCS minus 1 minus RCS on 1 plus RCS Vx. So ID is Gm minus Gm upon 1 plus RCS Vx. So this is your ID. Now if we observe, okay, what is I1? I1 is the current that is flowing through your capacitor CGS and resistor RS with a voltage of Vx connected from, like, for a potential Vx, which is Vx to ground. The I1 is flowing through CGS and RS. So I1 I can write as Vx upon RS plus 1 upon CGS, SCGS. SC. Yes. So I1 is Vx upon RS plus 1 upon CS. We already mentioned Ix as I1 minus of ID. So that is Vx upon RS plus 1 upon SCGS minus Gm upon 1 plus RS CGS S into Vx. So which becomes Ix equal to Vx upon Vx into 1 upon RS or SCGS into RS CGS S plus 1 plus Gm so your Z out is Vx upon Ix. So Vx upon Ix will become 1 plus RS CGS S by Gm plus S CGS. Now in place of S, we will basically substitute the omega, J omega. So S equal to J omega, that is J into 2 pi, what is that? 2 pi into 3.2 gigahertz. 3.2 into 10 to the power 9 hertz. So this will be substituted over here. This will be substituted over here. So what is the value of Z out that you are getting final after solving? So you have already found out the value of Z out. Now what is left is simply substituting the values of resistors, capacitors and Sj omega. So here Z out is 1 plus j omega RS CGS by GM plus j omega CGS. Now these are in real complex numbers, right? What is the magnitude of the output? It will be root over 1 square plus omega square r square cg square whole square by IGM square plus omega square CGS square root under. So what is the value that you are getting? Now the second question, this fourth question is again the same. Magnitude of output impedance of the circuit for the frequency has changed. So first the omega is 2 pi into 3.2 into 10 to the power 9 omega 1. Omega 2 is 2 pi into 28 into 10 to the power 3 radian per second, radian per second. So for these two frequencies, what are the magnitudes that we are getting? R is 43 kilo, CGS is 7.4 picofarad. For these given values, what are the magnitudes? So simply you have to substitute the values in this formula. GM is also given 1.47 millisiemens. So what is the magnitude of Z out for F equal to 3.2 gigahertz and magnitude of Z out for F equal to 28 kilohertz. This, what is the value of Z out for first? What is the value? Did anyone get this? Did anyone get this answer for first part? It is 42.99 kilo ohms for 3.2 gigahertz. Now in the same expression, we'll change 3.2 gigahertz to 28 kilohertz and again reiterate the calculations. So hope you can do this. What will be the value that you'll get if you do this? So here we are getting 681.337 ohms. So this is for high frequency and this is for low frequency. So if we observe very carefully how the Z out looks like. So Z out is like F or I can say Z out directly proportional to your F, right? Higher the frequency, higher the Z out. Lower the frequency, lower the Z out, correct? After solving these two problems, this is very clear, right? Higher the frequency, we are getting higher value of Z out. Lower the frequency, we are getting lower value of Z out. So they are directly proportional to one another. Now moving on to this problem. So here for the same common drain amplifier, like this was also common drain amplifier which we were analyzing currently, right? So for this circuit, the question is asked that given your observation of output impedance of the common drain amplifier circuits, what can be inferred about the quality of this output impedance? The output impedance is resistive in nature, inductive in nature, capacitive in nature, or is it very low value? So now, first of all, what is a resistive behavior? What is a resistive behavior? Z out, if it is a resistor, then it is not a function of, okay, so it is not a function of frequency. Correct? This is the resistive behavior. When we say it is inductive in nature, inductive means Z out will be somewhat of the behavior of omega XL. XL means omega L. That means directly proportional to frequency. Right? When we say capacitive behavior, that means Z out will be somewhat equivalent to XC, which is 1 upon omega C. So here it is inversely proportional to frequency, right? like I should not write it like this. So in this case, your Z out becomes inversely proportional to frequency. So what did we observe? We observed that from these two analyses, Z out is directly proportional to frequency. So Z out is directly proportional to frequency means your circuit shows an inductive kind of behavior for output impedance. So it is inductive in nature. Is this clear? How we got it as inductive behavior? Because here we observed that the Z out was increasing with increasing the frequency, so it is directly proportional to frequency. And in inductive behavior, we observe this directly proportional behavior with the frequency. So that's how your common drain amplifier shows an inductive response for your output impedance. Any doubts? Hope this is clear. So that's all for today. Like these all were the problems which were selected for today. So any doubts and any problem? Are the problems clear? So we worked upon like pole zero analysis and mirror circuits in today's session. So if you have any doubts, please feel free to ask. Else, we can break over here and meet next week again. So if there are no doubts, maybe we can break over here and meet next week. Meanwhile, you can go through the lecture notes as well as the video and let me know if you have any doubts in the next class, or you can comment under the YouTube, like on the YouTube video, or you can mail to me if you have any doubts. So that's all for today. Thank you for joining. Have a wonderful evening ahead, and let's meet again next week. So see you. Bye.